Hello everyone, thank you for tuning in to D News Plus today. I am Trace, and this is our new series on stars. Not like the cable channel or like famous people, I mean like literal, actual stars. Make sure you subscribe so you get all of the episodes in this series. You can also find us on SoundCloud and iTunes if you want to listen to the whole series squished into one episode. But this week, we're going to talk about where stars come from and how they form and how to classify them and what the first stars were like and when did they come about. And also a star's life cycle and what happens after stars die. We're going to answer all of these questions and so many more all throughout our series here. So stay tuned, but let's kick into it. You can literally see stars 100% of the time, day and night. I mean, sure, there are more at night, but you can see them all the time. They're always there. A star is, well, it's a giant mass of incandescent gas. It's a gigantic nuclear furnace. I don't know if you're a big fan of, they might be giants, but you should be because they're very educational. A star is a sphere of superheated glowing gas, and there's obviously more to it than that. For a detailed description of star formation, buckle up, because we're gonna go there. Stars produce light and energy from nuclear fusion. Nuclear fusion is what makes something a star, would be kind of like the easy way out, but this is D News Plus, so we dive deep. Nuclear fusion happens when two light elements are smushed together and then they become a heavier element. About 75% of the matter in the universe is hydrogen, 23% of it is helium. So most of the universe is made of those two things, 75 and 23. I mean, that's a lot of stuff. There are, of course, other heavier elements scattered throughout the rest of the universe, but those two specifically are extremely ubiquitous elements in the universe, and they are the basic components of stars. Gravity is what makes these elements fuse together. And it only works when there's a lot of it, because the elements are going to naturally not want to fuse. You know, two hydrogen atoms are both positively charged, potentially, and they're not going to want to smush into each other. You need a lot of gravity to overcome that repulsion so that they can mush. Stars form in what is called an interstellar medium, or ISM. ISM is just fancy talk for molecular clouds. Molecular meaning atoms that are bound together, and these molecular clouds are often called dark nebulae. The conditions for star formation in the ISMs are perfect because there's a lot of hydrogen, there's some helium, and there's a few other heavier elements, and they all coalesce into super dense regions of gas. Molecular clouds, for the most part, find stability after long periods of time floating around out in space until something acts upon them, right? A nearby supernova, maybe? A galactic collision that sends waves of energy out into the universe? Potentially something else with lots of energy shakes things up. When that happens, that energy is imparted into this ISM cloud. And then things get crazy. The events cause a gravitational disturbance, which makes the cloud begin to collapse on itself. It throws off that balance. And once the balance is thrown off, things start happening, I'm gonna say really fast, but really fast in a galactic way. Stars don't form in like 5 minutes. It takes a lot longer than that. They collapse on themselves because the force of gravity is pulling them in. As these particles get closer together, atom by atom, molecule by molecule, they're increasing in density and pressure. And that means more mass. More mass means more gravity, which means this process slowly accelerates. And as that happens, things start to get really complicated really fast. The nice thing about gases is we have something called the ideal gas law, which tells you that the temperature, the volume, and the pressure are all related along a gas constant, as well as how much of the stuff, how much mass there actually is. That can all be related. It's super awesome and mind-blowing, and it gets more and more complicated as there is more and more and more mass. But it still balances within the ideal gas law equation. Super cool. You can actually look up the math of that. We'll put a link down in the description for this really awesome paper from the University of Colorado that we found. It's really, really great. I can't really wrap my mind around all of the math while we're doing it because it's a three-dimensional sphere of mass that's slowly falling in on itself, increasing in temperature and pressure, while also simultaneously increasing in mass, but the pressure is also pushing out on it and the temperature is going up, which makes the gas more excited, which makes it want to expand further. It gets really complicated, as you can probably guess. But now we're getting somewhere, right? All of this gas over time has slowly begun to coalesce and get more and more dense and warmer, and it's the beginning of a star. Basically how our star formed and how every star formed that you can see in the night sky. We could stop here and say, okay, and then once it collapses onto itself, it becomes a star. But come on, man. There's so much more happening. The cloud's gravitational potential energy turns into kinetic energy. That way, the individual gas particles within the cloud are turning into kinetic and then thermal energy as they crash into one another and create all of this chaos. The cloud starts to heat up. That kinetic energy is also manifested into the cloud's spin. The spinning of the cloud begins. We've seen this before in our formation series. Everything in the universe is spinning. But think of an ice skater that pulls in their extremities. Or if you are in a rotating chair at your office right now, maybe, spin and then tuck in your arms. You will speed up. That's how this works too. This is called the conservation of angular momentum. In case someone asks you what you're doing, just say, I'm conserving angular momentum. So as it spins, the gases also begin to flatten out, creating an accretion disk, and then that continues to collapse on itself for a long, long time. A long, long, long time. Like, a long time. Stars are big, and they are full of gas. The smallest of these star-forming nebulae that we mentioned earlier are about 3 light years across. Inside of something that size, you'd have about 2,000 solar masses. Now, if you look at something like our star, it formed in one of these stellar furnaces, these little nebulae as well, and the sun has a radius of 700,000 kilometers. So it's 1.4 million kilometers across. 1 light year is about 9.5 trillion kilometers. So by the time something 3 light years across coalesces into 2,000 or so stars of our size, that's really, really dense stuff. I mean, we're talking 0.0000015 light years across. Eventually, the star begins to form at the center of that accretion disk. But it isn't a star yet. Not quite. It continues to form until the collapse starts to slow down. And that is the pressure acting on the coalescing molecules. It hits a point where it's too dense to keep collapsing, but is able to compete with the gravity, the mass. You know, the temperature and pressure are pushing outward as the gravity is pushing inward. And together they slowly begin to balance. That coalesced gas cloud becomes what we call a protostar, although it's still not quite a star. Protostars are not quite stars yet. They're still amateur stars. Once nuclear fusion starts, then we can call it a star. And that will only happen if there was enough gas and enough pressure and enough gravity and enough heat and enough energy to smush those hydrogen atoms together and overcome their repulsion. Once that happens, it kicks off and becomes a star. The whole process we've been talking about, by the way, is called gravitational contraction. It's a gas cloud collapsing on itself due to gravity. When the pressure within the star causes that temperature in the middle of it to reach 10 million degrees Kelvin, then remember that ideal gas law, the hydrogen gets to be helium. And once that happens, an equilibrium between the pressure pushing out, the explosive energy of that fusion, matches the gravity pushing it in, we get a star. Now, after all that, some stars never start their fusion. And some stars start fusion so violently, and they don't have enough gravity that they explode themselves. You know, you just end up with a pop. And then they might end up forming other stars. I mean, it's a super interesting process, and it's happening constantly. It's super cool. I mean, I guess technically it's super hot, but it's super neat. Whatever. There are a lot of different types of stars, though. Don't just go around thinking there's just one type of star. That's starist. Hashtag not all stars. There's a lot of different ways to classify stars, but mostly it comes down to 2 different things. Their spectra and their surface temperature. Spectra is the elements that they're absorbing, but we'll get more to that in a minute. There are 7 main types of stars. From the hottest to the coldest, or decreasing in temperature, we've got O stars, that's around 25,000 degrees Kelvin. B stars are between 11 and 25. A stars are between 7,500 degrees Kelvin and 11,000. F are 6,000 to 7,500. G are 5,000 to 6,000. K are 3,500 to 5,000. And M is anything colder than 3,500 degrees Kelvin. So we've got, in descending order, O, B, A, F, G, K, M. Super easy. Say it out loud, you can remember it. There's also a mnemonic that they use called "Oh, be a fine girl and kiss me," or guy. It's 21st century. But I think that's a terrible mnemonic. I think you'll probably agree. "Oh, be a fine girl and kiss me." Come on. How about Obama bit a friend's gorgonzola? Crazy, man. Crazy with a K. I don't know. That wasn't that good. Okay, I can do better. Occupational bathrobes are fairly great for kelp men. Okay, those were both bad. Tweet me your favorite mnemonic. You can find me on Twitter at Trace Dominguez. You can find the show at DNews. So O, B, and A stars, those are blue stars. F stars range from blue to white. G range from white to yellow. And K are from orange to red. M stars, or the coolest ones, are red. So just to kind of put it in perspective, a bluer star is going to be a hot star. A red star is going to be a cold star. And the white and yellow and orange stars, they're kind of in the middle. Right? So our star, if you think about it, is a white star. So it's kind of average. It's a, average star. So to differentiate the stars, astronomers look at what are called spectral lines. Essentially, it's a fingerprint looking for the atoms and elements and molecules floating around inside of that giant nuclear furnace. There are two types of spectral lines that we can look at. There's the emission lines, which are lines that appear as discrete colored lines, and they correspond with wavelengths emitted by an object. So think colored lines on a black background. Maybe there's a red and a blue and a green. And then there are absorption lines, which appear as dark bands resulting from wavelengths that are absorbed along the line of sight. So think black lines on a colored background. So the idea is these two things help us identify what's going on inside of a star. Let me give you an example. I know this is complicated. Stars didn't actually make it easy on us. O stars have singly ionized helium lines, either in emission or absorption. Singly ionized helium is an atom that has lost one of its electrons. So a helium atom without an electron, it acts more like hydrogen. It still has 2 protons in its nucleus though. B stars have neutral helium lines in their absorption. A stars have hydrogen lines. F stars have metallic lines because the cooler ones usually have burned a lot of things and mushed a lot of stuff together. M stars, for example, have bands of titanium oxide because they have a lot of very dense stuff inside of them. That's why they can't burn as hot. Hydrogen can burn a lot hotter, and helium can burn a lot hotter. So either way, I hope you're still with me. These are kind of confusing. There's a lot of different ways to categorize these things. Because those letters are not quite enough to categorize every star, stellar scientists also have subclasses that range from 0 to 9. And they will combine the letter and the number. So a star that was halfway between an F0 and a G0 would be an F5. So you might have an F star, which is, as you may recall, a star that's a bluish-whitish star ranging from 6,000 to 7,500 degrees Kelvin. A G star is a whiter, yellower star, and it's a little cooler, ranging from 5 to 6,000 degrees Kelvin. So if you have an F5, then you have one that's in the middle of those two things. It's a little whitish, it's a little cooler than its other more bluish F stars, and it's an F5. So that way you can kind of break it down. Another example to kind of hit it home for you is the G star, 5 to 6,000 degrees Kelvin. It's a whitish, yellowish star. Our star is a G2. So it's on the cooler side of the G spectrum, and it's more yellow than it is white. That's not the only classification that we have for stars though, because science likes to be as specific as possible and make things as complicated as it can. So then you have luminosity. Luminosity is the amount of energy being given out by a star, the amount of light, if you will. And we classify those using what's called the Yerkes classification, or MMK, based on the initials of the authors. And this scheme measures the shape and the surface gravity of stars. So from that we get 1A, which are most luminous, usually supergiants, 1B, less luminous supergiants, 2s, which are luminous giants, all the way down to main sequence stars, which are 5s, and dwarf stars, and so on and so forth. The reason they call them main sequence is that they make up about 90% of all of the stars. Our star, a little more specific still, G2V. So our star is a main sequence type star, or dwarf star, that's in the middle of the road temperature-wise. Not super white, a little bit yellow, kind of on the cooler side. G2V. I don't want to get too listy on you, so I think we're going to end there for today. But tomorrow we're going to talk about what does it mean to be a star? Because now we've talked about how you've created the star, and we've talked about what that means in terms of your classification. But what do stars do? Like, why do I care? Why do I care about them? Tune in tomorrow to find out. You can also subscribe so you get all of the episodes in this series. But before we go, I want to take a minute to thank our sponsor for this episode, Great Courses. If you like learning, like obviously we do because we work here on DNews Plus, Great Courses gives you on-demand access to a huge library of really awesome video courses from experts in their fields. One of those being super famous astrophysicist Neil deGrasse Tyson. He did a thing called Inexplicable Universes. It's on Great Courses. It's super awesome. You can check it out. You can help us out by signing up today for your free month of unlimited access to Great Courses. All you got to do is go to thegreatcourses.com/DNewsPlus. There's a link down in the description, and you can check out all of this really awesome educational stuff. Super fun. Thanks so much for tuning in to DNews Plus today. I'm Trace. We'll see you tomorrow.